Now we want to look at the energy situation for a simple harmonic oscillator. If we have an object of whatever mass at a position x relative to equilibrium, where the object is moving from an extreme point here to an extreme point here, amplitude A, then we ask what's its kinetic energy and what's its potential energy at this point. If we can answer this question, we can use the kinetic energy expression to obtain an expression for the velocity of the object. Now, this simple harmonic oscillator is driven by a restoring force F equals negative kx. If we have this law, or this force relationship, then the potential energy at position x is 1/2 kx squared. And we've seen that earlier in the course. We see that fairly easily. If we move from here to here, we move from zero force up to force that's equal to kx. The force we have to apply will be kx. The force exerted by the restoring force will be the negative of that. But the average force we have to exert to move from here to here and do the work that gives us our potential energy will be positive. So we'll go from 0 to kx. Since the force is linear, we can get the average force just by averaging the initial and final forces, and we find that the average force is 1/2 kx, so that the work done in moving from here to here is average force times distance. The distance is x, and we end up with the work equals 1/2 kx squared. We also note that the maximum potential energy, the potential energy if the object is out here, is 1/2 ka squared, where a is just the x value of the position at the extreme point. So we pull this thing out to the extreme point, its energy is all potential, there's nothing moving. We release it and the potential turns to kinetic, and then we pass equilibrium and the kinetic goes back to potential, and we keep going back and forth between potential and kinetic energies. So, if we move from the extreme position A to position X, what's our change in potential energy? Well, it's going to be the potential energy that we end up with minus the potential energy we started with. Now, just intuitively, do you think the potential energy is going to increase or decrease here? Well, there's more potential energy here than there is here, so it's pretty clearly going to decrease. If we subtract this kinetic potential from this potential, we get 1/2 kx squared minus 1/2 ka squared. We can factor out the 1/2 k and get this expression. And note that since a is bigger than x, this is negative, so our potential energy change certainly is negative. Okay, potential energy is lost because x is less than a. Our conservation of energy, if we assume that we have a well-greased oscillator that doesn't lose any energy, doesn't dissipate any significant amount of energy, at least over the time we're observing it, we can say that the change in potential plus the change in kinetic energies is 0. And this just simply states the obvious, that whatever potential energy is lost is gained in the form of kinetic energy. So our change of kinetic will be negative the change of potential. If we take the negative of this thing, notice that I've reversed the a and the x, and that's equivalent to taking the negative here. The x becomes negative, the a becomes positive. We just distributed negative sign through here and we get this. So this is our change in kinetic energy from the extreme point at A to the point at X. Of course, at the extreme point A, our velocity was 0. So we had no kinetic energy. At point X, we've got a velocity, which we're going to call v, and the change in kinetic energy is therefore just 1/2 mv squared, since we started with 0 potential energy. And we see then that our 1/2 mv squared will have to equal the negative change of potential energy, the 1/2 k times a squared minus x squared. The solution comes out very easily. Multiply the 1/2 out or divide it out, whatever. We get the square root of k over m times a squared minus x squared. Now we notice that this square root of k over m is just our omega, our angular frequency. So we can do a little bit of rearranging and simplifying. We restate the conditions. If f equals negative kx and the maximum x is a, then the velocity at x is square root of k over m times a squared minus x squared. We just obtained this expression. Since the square root of k over m is omega, we can write this here. And you can verify for yourself that if we factor a squared out of this, we get this. Just multiply this out and you'll get this. And that'll convince you that this is a valid step. And then the square root of a squared will come out of the square root and become an a. And we end up with this expression. Then we note that omega a is just our maximum velocity. So our velocity at point x is just our maximum velocity times this square root. Now what's this square root? If x is 0, that means we're at equilibrium. This will just be 1, so we'll have v max. The velocity is v max at the equilibrium position, which we know. If x is equal to a, then we get 0 here, and we get a velocity of 0 at the amplitude a. And that makes perfect sense too. That's consistent with our experience of pendulums and other simple harmonic oscillators. If we're between x equals 0 and x equals a, we take this ratio, x over a. This is just how much of the distance we are from the equilibrium out to a. Half the distance, 3/4, 5/8, 30%, 10%, whatever. This quantity is going to be our proportional distance between x and a, or between equilibrium and a. And we square that and subtract it from 1. And we get this square root, and that's the proportionality of our velocities. So if we just think of this as a proportionality factor that gives us the velocity in terms of the maximum possible velocity, we can attain some pretty good understanding of the velocity function.